We start today a new series of videos in which we will describe acidic and basic character in organic compounds. Acids and bases can be distinguished by two concepts: Bronsted-Lowry concept. According to Bronsted-Lowry, those compounds are acids which can liberate proton, that is, proton donors. Proton donors means which can liberate proton. These are HCl, HNO3 and other inorganic acids, or organic acids like formic acid, benzoic acid, etc. They all have capacity to lose proton. Bases are those which are proton acceptors. Like H2O, they all have electron pairs here, ammonia, and other compounds having hydroxy groups like calcium hydroxide, barium hydroxide, etc. These OH ions, ammonia, water, all can accept protons. So, in broad, these can be distinguished by proton accepting or donating capacity. Another definition is from Lewis. According to Lewis concept, acids are those which can accept an electron pair. It is not necessary that they should have a proton. They must have capacity to accept an electron pair. All cations R plus, NO2 plus, Cl plus, etc. Zinc chloride, it has vacant d orbitals. This can accept proton electron pair SnCl4, Bf3, etc. They come under the category of Lewis acids. They all have a capacity to accept an electron pair. Bases, on the other hand, are those which can donate an electron pair. So, all anions are bases according to Lewis concept. We will discuss bases after we have finished discussing about acidic character. So, we switch over to acidic character now in detail. As regards organic compounds, we observe only Bronsted-Lowry type acids. So, we will concentrate on this. Let us take HA. This compound has one hydrogen here. If it is capable of losing this proton, there must be some medium, and aqueous medium is ideal for this. You are left here with A minus anion. H2O accepts this proton, forming H3O hydronium ion. A is the conjugate base of HA. We will use this term frequently, so understand this. And H3O is the conjugate acid of H2O. This is in equilibrium. In inorganic gases like HCl, HNO3, etc., they are 100% ionized, and this reaction is not reversed. Whereas, when there is partial dissociation, which is frequently with organic acids, the reaction is in equilibrium. So, there is a percentage dissociation, and the degree of dissociation, which is called, greater the degree of dissociation, more is the formation of these. This dissociation is measured by a constant Ka, ionization constant. I will not go in detail in this, you will read this in physical chemistry. And there is term pKa. This is negative of the logarithm of Ka. Greater the dissociation, more is the value of Ka, but this is reversed. Greater the dissociation, degree of dissociation or ionization, greater is Ka and lesser the pKa. So, inorganic acids have pKa minus values up to 2. Less than 2, they are all inorganic acids. From 2 to 10 pK values, you have organic acids. So, greater the pKa, less is the acidic character. You must remember this. We will discuss this acidic character in terms of pKa in our discussion. We now take organic compounds and discuss whether what brings acidity in them. So, you remember always that an organic compound is acidic if it is capable of losing a proton. When this will be capable, that is the anion or conjugate base left after proton loss is more stabilized means less reactive than the compound itself. For example, if you take RCOOH, this is lost as proton only if this conjugate base if what is there, this will be H3O. This conjugate base must be stabilized and more stabilized than this. You can write these two resonating structures. Whereas here you could have written this structure. Here there is stabilization, but lesser stabilization, because the two contributing structures, one of them is having charge separation, that is of high energy. Energy of the two is not same. I told in my resonance lecture that equal the number of resonating structures of equal energy, more is the stabilization. So, this system is more stabilized due to resonance, because unless this is of lower energy than this, it will not be formed. A product cannot be of higher energy. So, carboxylic acids are acidic in nature because the anion left is stabilized. You can see this example. This also has ROH, yeah, OH here like this, but if you write this loss of proton like this, alkoxy ion, this has nothing to stabilize this system, CS3 or C2H5 etc. do not stabilize it. So, this is unstabilized. Therefore, it is not acidic. This ionization will not take place. On the other hand, if you take phenol, phenoxy ion, we want to see whether this is possible or not. This would be possible only if it is more stabilized than this, and it actually is. You can write several resonating structures for this. Etc. You can write all this. So, in phenol, if you write these structures, there is a charge separation in these structures. You can write many more. This makes the system less stabilized than this. So, this conjugate base is more stabilized, hence this is possible. So, phenol is acidic in nature. If you take case of methane, this is not acidic because this conjugate base not stabilized. One more example, if you take cyclo pentadiene, this has 2 hydrogen atoms here. You want to see whether this is acidic or not. If you lose a proton, you are left with an anion here, electron pair here, cyclo pentadiene anion. You see, this is stabilized like this. And so on. And so on. You can write 2 more structures. Here there is no stabilization at all, only 2 double bonds, sextet is not formed, no deregulation of that type. So, this is more stabilized than the compound itself. And this compound is acidic, pK, though weak acid, yet it is acidic. This way you can judge which compound is acidic or not. In the next, we will describe, we will take these examples and show how the acidic character increases or diminishes.